great reason to finally come to Berlin, first time here. So very happy to be here and look at the city a little bit. In the keynote yesterday from Kostas and Stefan, in many of the sessions, at least the sessions I went to, there was a lot of emphasis and excitement around the use of Flink for stream processing. And that's really what makes us at Google so in love and interested in Flink, because we feel like it's a soulmate in that sense. We've made that journey internally from batch to now continuous processing using a string model. We've made that journey internally. We're also made it in what we offer to the outside with Dataflow that I will describe with our cloud services. So really, the concordance of spirit between Flink and Google in that sense is excellent. In this session, I'm just setting up the example I'll be using to try to explain the concepts that we introduced in the Dataflow API. So, silly example, it's a mobile game. People playing all over the world in teams. So you have the green giraffe team, for example, and they're very widely distributed all over the world. And so I mentioned that because their events are going to arrive not necessarily in order. That's the point here. And then other teams like the monkeys and the whatever those things are, pandas or raccoons, which are more geographically aligned. So that's a silly example. We don't care what the game actually does. What we care about is that on the back end, we're going to want to do useful calculation on those events in real time as they happen. So I'll break that in a few sections. And so let's start with the very basic. These are the data points. Each one of those is something happening in the game on somebody's phone. And let's say the caller represents the team they're part of. And you want to do something with those events, something as simple as just adding all the points from all the players in the same team to see how well that team is doing. So we get these data points, that's great. And our game is awesome and our game is popular, so we get more and more data points. And we get, every day we get a new batch of data points. And so it's growing, but in reality, this is not the right way to think about it. It's really the way the events are arriving. It's just a continuous stream of events. The end of the day, wherever you are, in California or in Berlin, means nothing to your people playing your game, in Singapore. And so the way to think about it is as that stream of events, but that obviously comes with some clear challenges. So delays, I mentioned that players are all over the world. So at 8 o'clock, this event happens, which arrives. So this is the time at which your pipeline sees the event. And this event arrives pretty close to when it happened. And this other one arrives a bit delayed. This last one, that one happened at 8 o'clock. It actually arrived hours later. Maybe the user was playing on a plane in airplane mode, or skiing in the back of the mountain and with no network access, or just camping in the woods for a week. And so that's the reality. That's the kind of events. You may not get things quite that late, but you definitely get a lot of time differences. And in the end, that's the real life. You just cannot fix that. What you have to do is be explicit about the compromises and the trade-offs that have to be made. And have a tool that allows you to be very explicit on how you want to balance things. And so, completeness. We saw that events that arrived hours later. Obviously, I never know. Some events could arrive even later. So if I just wait to be sure everything is there, I never process anything. But if I process too early, I lose completeness. How do I deal with that? Latency, that's the flip side. How quickly do I want results to come back? And obviously, cost, how much do I want to pay? And along those three dimensions, different use cases position themselves differently. So if you're doing a monthly billing pipeline, you really, really care about completeness. This is money. This is the money you make. This is the money your customers pay. So it has to be complete. Latency is not a big deal. The bill comes once a month, maybe 5 days after the month closes. Latency is not an issue. And cost, you don't really having it low cost is not that big a deal. This is something really important for you. If you have to pay more to get it right, you'll pay more to get it right. And so for that use case, these are the trade-offs you want to make. If, on the other hand, you want to give your users kind of a running tally of how much they've spent so far, you care less about completeness. It's an estimate of their bill. So if you're missing a few transactions, that's probably acceptable, as long as it's still in the bulk. Low latency, that's the whole point of the service. You tell them quickly where they are, and you get as much events in as possible. And you probably don't want to pay too much for that because this is not something that actually makes you money. It's usually a free service that you want to give just for a customer experience. Now, if you're looking at things like abuse detection, like back to the game, let's assume the players interact, and some players may cheat or they may harass each other and just make other people miserable by their interaction. Now, when you try to detect those, latency is the most important thing. Because if it takes an overnight run to figure out the abusers, well, they've had hours to harass people, and you've probably lost those people, those users, before you've been able to do anything. You don't really need completeness. Like, it's mostly heuristics anyway. If you're missing a few events, it's not going to change very much to your algorithm to detect abusers. And this is important. So you don't really need to optimize for cost if you can do a good job. So again, a completely different set of trade-offs that you want to make. And then on the same topic, and probably the same code, the same algorithm that you're running here to do real-time abuse detection, you may also want to run it on historical data, looking at all your logs as a way to find long-term trends, as a way to validate and train your abuse algorithm. And in that case, it's very different. You don't care about latency anymore. You're just doing a run on historical data. You care more about completeness, but actually it doesn't have to be perfect either, because again, you're training an algorithm that's going to run in stream mode. You care a lot more about cost, because this is really large data sets which you're going to run over and over again, and so you probably don't want to spend too much on that. And so that's a good example of the same pipeline, depending on the context in which you run it, having completely different trade-offs between latency and cost and completeness. And the last thing you want to do is to have to write your pipeline twice to be able to do that. A, because it's a lot more trouble, and B, because it defeats the point of testing your algorithm if you have to implement it twice. Because you may think it's the same algorithm you've implemented twice, but in reality, code written two different ways is never quite the same, never has the same bugs. And so these are just illustrations of why it matters. Like there isn't like a good system that does everything right and a bad system. This is about giving developers and giving people running operations the right tool to be very explicit on the trade-offs they make and how they want things run. And so obviously at Google we got to that over the last 15 years, starting when the first thing you do as a company is to index the web, obviously scale is an issue. The first problem you have to solve is just run things at very large scale. And even though the web of 15 years ago was not nearly as big as it is today, it was still a big scale challenge. And so a lot of the early work, MapReduce and things like that, was all around getting scale. And at this point, it's a given. Like, when you say Google, YouTube, Gmail, search, like obviously scale, that's obvious. That goes without saying. But that's really not the hardest problem. So scale is what, gives huge data center, and you can see them, or you can draw a map of fiber connections across the Atlantic, across the Pacific, and so that's there, that's visible, that's something we think about. The stuff that's actually more important is to do that efficiently, and I mean efficiently in terms of the hardware, the resources, the energy that's consumed, but also efficiently in terms of the developers and the SREs, the admins, the productivity of developers. Because in the end, if you just solve for scale and you don't solve for cost and productivity, it's a very different company. So if every Google search cost Google $1 to process, it'd be a very different company, very different business. So the productivity and the scale at low cost is really the hard part. That's where most actually of the innovation is going now. It's not necessarily scale as much as real productivity. And so one of the ways you see that coming out is in that series of papers. Sorry, you probably can't read the white on gray. You know those names: Google File System, Bigtable, Dremel, Pregol, Colossus. Those are papers that Google has published based on tools and frameworks developed internally. I've highlighted the blue ones because they are those most relevant to Dataflow, to what we're talking about today. Because those are the innovations around large-scale data processing, starting with MapReduce, and then Flink Java and Millwheel. And those together turn into Dataflow. And with Dataflow, we've really changed the pattern. It used to be Google would develop technology, at some point publish a paper, and just like, here's a paper, do what you want with it, like we don't care. we're already working on the next thing internally. And so a lot of open source implementations, HDFS based on Google File System, Hadoop based on MapReduce, Edge-based based on Bigtable, etc. Open source implementations, which took those papers and say, hey, let's do that for everybody. Let's implement it. And Google's like, yeah, fine, we don't care. That was the approach. With Dataflow, we're really changing that around. And so with Dataflow, we're not just publishing a paper. But actually, the first thing we did is to put an SDK in open source back in December of last year. And then we rolled out a service in April of this year, a cloud service implementing support for the SDK. And only recently, in August of this year, did we actually publish the paper. And part of that is just the time it takes to be accepted. So the paper was published at VLDB in August of this year. And that's really the pattern now that we're in. Now that we are, as a cloud company, we're not just about just sharing innovations randomly. We are about bringing things to our customers, bringing it to everybody with a sense of purpose. And so that's why we started with the open source SDK here, and that's the pattern you'll see. You see that with Kubernetes as well. If you follow kind of container orchestration, that's the way Google is now engaging. So, kind of the journey there, the usual. So we all know about MapReduce. You get all your events, and then you have a map phase where like let's say that you assign a shape to each of the event in parallel. So this one is a circle, that's a triangle, that one is actually, all right, completely off topic here, but I was going to say that one is a diamond, but actually it's still a square. And actually I got into a fight with my son's teacher in elementary school earlier this year because he had to name shapes, and there was a square like that which was tilted, and he said square, and she's like, no, it's a diamond. And so actually, he was very distressed. So I actually had to go talk to the teacher saying, sorry, that's a square. Just because you turn it doesn't mean it's not a square. And the teacher would not agree. So anyway, completely off topic, but I was raised in France. We care about math. I know people in Germany care about math as well. In the US, it's embarrassing, frankly. Until you get to university level, math teaching is embarrassing. So anyway, completely irrelevant here, but just seeing that twisted square just gives me a flashback to that discussion. So anyway, we have our mapper who assigns shapes, and then you shuffle it, and then you have the reducer, which takes everything of one shape and does something useful with it. Figure this is kind of a nicer example than doing a word count, which is kind of overused. So this is a good visual way to think about MapReduce. And so MapReduce is great. It's a great hammer. And for many, many years at Google, we banged a lot of nails with that hammer. We're like anything that was a bit over the surface, we just MapReduced it. And good engineers can do a lot of things with a hammer. And so there's lots of things that were reduced to MapReduce. But we spent a ton of time not just writing it MapReduce, but optimizing it. Because if you write it naively, you get really, really bad performance. And so we got some of our engineers got really good at it, but that really was not a good use of time. And so what emerged as a response to that is Flume Java, which has nothing to do with Apache Flume. The name kind of is confusing. That's just the internal name. Actually, we published a paper by that name, which is a way to express your computation as a DAG, which then gets optimized by the tool. And then the original one was just, at the end, it was still MapReduce. It was compiled to MapReduce. But you, as a developer, had a much more expressive way to express your computation. And we could use all our kind of collective learning to optimize it, as opposed to individual developer using their experience to optimize their MapReduce. And so that's Flume Java. And then later on, we moved to have it not compiled to MapReduce, but run the DAG directly. And that's great in the sense that it gives a much higher programming abstraction to users, but it's still batch mode. So whether it's MapReduce or Flume Java, it's great when you have a finite collection of events. You just run your processing, you get the ordered results. Day after day, you can repeat that, and you get the batch for every day. If you want to get more fine-grained results, well, you can do that in your processing. You can say, as part of my daily processing, I'm going to group things, in hour. And so, at the end of the day, you run your batch, and you get things sorted by hour, which, gives you more fine-grained visibility. But you still have the issue, like the latency issue, for example, that, you wait till the end of the day to get your results for what happened in the first hour. So you wasted, 23 hours for nothing. You also have the issue that a lot of the grouping doesn't necessarily map to time-based groups. And so things like sessions, for example, your users don't care that the clock rings in your office that says, that's when the batch starts. Like, your users do things continuously. And so here, some sessions just, out of luck, happen to map well to one day or the other, but in the general case, sessions don't map well. And so you end up having those broken sessions that, are not, do not really correspond to user activities, or you have to do a lot of logic in your own program to deal with that and keep state and put things back together, which complicates the business logic. And so to solve that, another tool that was developed internally is called Millwheel, also published as a paper for continuous processing, which manages all the workers and orchestrate the computation of your DAG. And that works great when you're doing things like this, just filtering. And so you just have events, and you don't really have to maintain much state or group events. You just want to pick some events and let them go and stop the others. Or some other patterns, like when you want to do key-based lookup. So I have a request, I have a response. I'm waiting for the response with the same ID as the request. And so there are patterns like that work well. But most of the time, you really want to do things based on time. And so kind of the obvious step is, well, it's micro-batch. It's I'm going to do the same thing I do in batch, just much smaller batches. And so, I take the events as they arrive, and then every, 10 seconds, 30 seconds, I call that a new batch, and run that through the system. But in reality, what you care about is analyzing things based on when they actually happen. Most of the time, that's what matters. And so you have to map that from the event time to from the time when you receive it, the processing time, to the event time when they really happen. That's critical in many cases. So we have, as part of our internal security, we have plenty of pipelines that get data points from everywhere. And so just desktop security. I have an agent on my machine, which once a day reports to Google Corporate what's running on the machine. And then, whenever I make a call, it goes to the Google proxy, which, in almost real time, knows, if I try to make some suspicious connection. And so the security team then has to look at, their algorithms have to look at all my proxy requests, which they get almost right away, and then once in a while they get a dump of what's installed on my machine, and they have to look for suspicious patterns or flash exploit and things like that. And so they have two streams of data which are very, very different arrival time, but what they care about is comparing them based on real event time. And so in a micro-batching world, it's not impossible to do. It just means you as a developer, you have to do that all yourself. That becomes the logic you write, and hundreds of lines of code to wrangle things and manage that by yourself. Same thing with sessions. We got the example here. What I really want to, if I'm analyzing sessions, these are the buckets I want to get, already sessionized, and I just want to write my logic and let the framework do the hard work of deciding what are the boundaries of a session and how to assemble things together. And so to make those things work, the first realization is just to make it very clear. There are two different events. There is the event time, when things actually happen, in yellow here, and there is the processing time, when you actually get those events in your processing pipeline. And once you've called them like that, it really helps you start to think about, okay, then how do I want to manipulate that? Because both are real things, they're real concepts, and I have to deal with them. And the thing that helps you understand how to deal with them is the notion of skew, and the realization that the skew is variable over time. And so the tool that we came up with to help you deal with that is the watermark, which is mostly heuristic based. It's the systems kind of doing the work for you of trying to infer and guess when how that skew is doing over time, and when when events are most likely to have been received. And I'll show later how in the programming model we use that to great effect to help with the processing pipeline. So that's the Dataflow model. Everything I described here is actually very similar to what's coming up in Flink 0.10 that has been discussed yesterday, and I assume will be there more today. The key of the programming model is really to break the concerns that the programmer has to deal with in 4 different questions. The top 2, this is where you as a programmer, you live in an ideal world. You live in a world in which events arrive to you as soon as they're emitted. They always arrive in order. It's the perfect world that we all dream to live in. And so you get the luxury of living in that perfect world as you implement your business logic. You describe just what you want to do. It simplifies your business logic a lot because, again, programming the perfect world is much easier. And so the what, that's your computation. Like, what do you want to run? So, in our case, the what may be as simple as I want to add all the points of all the members of each team. Like, that's the what. Obviously, the what can be a lot more complex, but you just, you describe your algorithm. And at the time when you write that algorithm, you do not have to decide if you're going to be running in batch mode, in streaming mode, if you care about completeness, if you care about latency, if you care about cost. Like, you're completely isolated from those concerns. You just have to capture your business logic. Where in event time, again, you're still in the perfect world in which things arrive as soon as they happen. And so you get to tell us in event time, how do you want things grouped? Do you want them by, windows? Do you want them by sessions, etc.? And then the other 2 is where the ideal world in which you write your business logic gets mapped to the real messy world in which things are not in order, in which you cannot always predict when events arrive. And so in yellow, when is when you describe, okay, when do I actually run my computation? When in actual processing time can I run? And what happens when things get messy, when I get late events, etc. So that's really the way I will describe each of those 4, and they each, in the API, they each correspond to a different part of the API, very well isolated. But that's really, keep in mind, that's the logic. What you want to compute in event time, what do you care about? And then the messy world. When can I actually compute, and when do I do when things don't map to what I expect? So the what, very similar to Flume. It's a DAG. It's a very convenient way to describe your pricing pipeline. The 2 key concepts are P collection, which is a set of elements, bounded, unbounded. It's a logical object. It could be, it's backed by a data source. Maybe it's a topic or a queue. Maybe it's backed by a directory. And a directory, maybe that's a bounded data source, like, process everything in that directory. Maybe it's unbounded because somebody keeps putting files in that directory and you're continuously processing them. P collections don't care. They're not tied to a bounded or unbounded model. It's the same object. And that's why your business logic gets reused between batch and stream, because the P collection doesn't need to know if it's bounded or unbounded. And then the way you deal with P collection is via P transform. So P stands for parallel. Parallel collection, parallel transform, because obviously these are executed in parallel. And so there's a set of P transforms. You can do element by element transformations. You can do aggregation, group by keys, things like that. And you can create composite transforms, which are made of other transforms and themselves can be used. So you can build libraries of transforms that way. And so these are the 2 kind of basic mechanisms for describing your computation. Again, the what. Then there is the, let me stand that for a minute. So this is great, and let's run this in batch mode. So again, our graph of event time, when things actually happen, and processing time, when we receive it, and the dotted line, that corresponds to the ideal, where everything would be on the line because everything would be received right away. No, it doesn't go to the center because the time axes are shifted. Like the yellow one starts at noon and the other starts at 12:05. So that's why it looks kind of weird. And so, our events are not, on the line because this is the real world. So, number 3 arrived pretty quickly. That event, number 9, is very, very delayed. And so that's the real world. When you run that in batch mode, it doesn't really matter which order. You just get all of them, and then you process, so you add them all. And then when it turns blue is when you emit the results. And so as a user, I basically know nothing until my batch completes. And then I know my results for the entire batch window. And I know, okay, boom, 51. That's the batch mode. That's the first step. As we said, most of the time, you actually want to aggregate events, and you want to analyze them in a smaller context. And so Dataflow provides, we call those windows, provides windowing mechanisms already integrated in the framework. And so you may want fixed windows. I want to group everything by 1 minute time chunks. You may want sliding windows. Every minute, I want to get the average of the last 3 minutes. Or I want to get all the events in the last 3 minutes in my window and then do whatever I want with them. Sessions. These are the 3 most popular. There are other windowing mechanisms, or you can create your own if you want to, but that's pretty rare. Most of the time, most problems can be reduced down to some of the main windowing mechanisms. And so in code, basically what you do is you just tell the windowing you want to use. So the middle line here says, I want to window things in fixed window of 2 minutes. And then the last line is basically the calculation you want to do, which in this case is just do a sum of all the values. And so just by adding that in your pipeline, you're not modifying the code you wrote previously, the transform code in blue, which here is just a simple addition. Like that code can be very complex. You don't have to go and modify it to inject the notion of subdividing into windows. That code doesn't change. All it does is it adds up all the points. And then the subdivision is something you inject in your pipeline without changing that code. And so now, we still run in batch mode, so we don't turn blue until the end. There, now we're blue. So we still run in batch mode, but because we've injected that windowing, when we get our results, we actually get our results calculated for each different window. And by the way, here, this is one team. So everything here is whatever, teal, whatever that color is. Imagine that happening in parallel for every team, because again, you've asked to group by key, the key being the team ID. So here we're just looking at one team, but this happens in parallel across all the teams. And so now, okay, great. We've added windows, but we still haven't dealt with the latency problem. If you look here, if you look here, the results only arrive at the end of the batch window. And so trigger is the mechanism that we have to get results earlier. At some point, I'm pretty sure I could get the total of everything that happened from midnight to 1 a.m. I'm pretty sure I don't have to wait until midnight the next day. I can get that early. And so trigger in the API is how you as a programmer make that happen. And so this is how you add a trigger. It just, again, one more line says, please trigger. So trigger just means don't wait to do your calculation. Trigger at some point. Now, when do you need to trigger? Well, here, we're saying trigger at watermark. So remember the watermark? This is the system's estimation of when of the skew between event time and pricing time. And so actually that line you don't even need to put it because that's the default. But for clarity, I've put it here. I say trigger at watermark. And so from now on, we're going to get our results much earlier. So you see the 5 turn blue much earlier because as soon as the watermark reach the time, say, okay, I trigger and I get my events. And so now, I have stream processing. I can actually see my results happening, with much lower latency. That's great. There's obviously 2 issues here. The obvious one is the 9. No, the 9 arrived very late, and I had triggered already. So the window, that first window had triggered, and then its late event arrived, and so I don't have completeness here. I only have, whatever data was available at the time when I triggered, which is, the compromise I made to get low latency. The other issue is if you look at the third window, I could actually have triggered much earlier. So, after I got that 3, I still waited for a while because my watermark was not aggressive enough. So, sometimes it's too aggressive, sometimes it's not aggressive enough. That's obviously, that's the nature of the real world, but that's how you can start to get low latency. Now, how do you deal with these 2 problems? Well, the way you deal with them is by having a richer trigger mechanism. And so you can say, in addition, I want to trigger early. That 3, I could have calculated earlier. Even if the watermark doesn't think that we've gotten all the events, maybe I want to force an early trigger. And so here, we add a line that says early firing, and we say, trigger every minute. Like, no matter what the watermark says, I want you to trigger every minute. Just give me early results. And to handle the case of the late event, we're adding a line that says late firing. And so if, at count 1, so only takes one event. Every time you have a late event, I also want you to fire again, such that that late event can be incorporated in my calculation. And so now when you run that way, you still fire early for the 5, but then you fire again once you hit the 9 to give a chance for your pipeline to just say, hey, there's a late event, I'm going to do something with it. In some cases, you actually don't want to do that. You just want to ignore late events. They're irrelevant. That's fine. You get to make that choice explicitly. If you want completeness, you have a tool to do that via trigger. Same thing for the 3. We now trigger much earlier because we got one of those every minute trigger, which happened after we got the 3. So we did not have to re-trigger after that. And so this is the way that without modifying your actual business logic, the what, you're just adding in your pipeline a request to trigger early and to be able to handle late events. Now, obviously, as soon as we do that, either have early triggers or have late events, that means that the same window triggers more than once. And so what happens then? Like, how do you want to deal with that? Well, it really depends on what you're doing and what's downstream. What are you writing to a database where you can do updates? Are you sending emails? Which all you can do is send a correction email. You cannot recall your email. So depending on what you're trying to do, you have several refinement strategy when you get successive firing on the same window. And so here, let's assume that we get, like as we were doing speculative triggering, so before the watermark, we got a value of 3. And let's say here we're just adding stuff, we're just adding points. And then, before we got to the watermark, we got a 5 and a 1. And that was the watermark. And then we got a late event. So we've triggered 3 times. We had the speculative trigger with only the value of 3. We had the watermark trigger with 3, 5, and 1. And we had a late trigger with all those plus a 2. And so one thing we can do is discard. So if you're writing to something that you can add to, you just tell the system, when you trigger a second time, don't give me the old events. Those have been taken care of already. Just give me the new events which arrived since then. And so that's called discarding. And so you can tell your counter, hey, add 3, add 6, add 2. And you rely on the counter keeping track there. Or you can accumulate. You can say, actually, I'm going to send a new email. That's not a very, very common example, but that's an easy to understand one. Every time I trigger with new data, I just want to give the complete accurate, at least accurate as of this point in time, result. So just give me back all the data, and I'm going to resend everything. And so that's the accumulating. Or you can accumulate and retract. You can say, no, I have to fix stuff. I have to tell my downstream processor to undo some operation and give them the new value. And so again, you decide based on the semantics of your application and the capabilities of your downstream pipeline. But you get to make that choice explicitly. And again, I'm repeating myself. You do not have to change your algorithm, to change the actual transform that happens in order to adapt that pipeline. And so here, we're going to say, we want to accumulate and retract. So when you do a recalculation, we want to send, a negative 3, remove 3, and then add the new value, which is 9. And while we're at it, just to make things even more complicated, we're going to change our windowing strategy. So until now, I was windowing based on 1-minute events. Now I'm going to window by session. And so let's see what happens now. It gets a little messy, graphically at least. But what happens is, as I start building, I'm assembling my sessions. And if you see at the beginning, it feels like there are 4 sessions. 1, 2, 3, 4, 4 sessions. And then at some point, I get an event, I think it's the 3, which joins those 2 sessions here. So like see these two sessions here actually turn into 1 because I get an event which tell me actually it's the same user session, like the user did not go away. We just did not see that event until later. And so you can, using that retraction mechanism, you can say actually, there used to be two sessions, now there are only 1 session. Again, that's an example, graphically it gets a little confusing, but just to show kind of the power, the semantic power of the API that lets you make those choices, those decisions by yourself explicitly. And so that's basically the build up to that. First you just do classic batch, calculate everything in one go. Then you add windows to your batch. You still calculate in one go, but you get your results windowed, which is usually more useful. And then you start to deal with optimizing for latency. And so you stream it. At number 3, you're streaming, but you don't have completeness anymore. You just, you've traded that off for lower latency. Number 4 is when you have the option of having both. You have low latency results, but you also get completeness because you can handle new results when they arrive. And 5 is what gives you the mechanisms to actually productively manage that situation in your application. And so that may sound very complicated because now you have to think. Oh, now I have to think, what do I do with late events? But in reality, these are trade-offs you're making today. No matter what code you're writing, the late events, they're happening. Maybe you're ignoring them, or maybe you're writing complex business logic to try to take them into account. But even in batch mode, those things happen. So this is not actually complexifying things. This is just making explicit the decisions and the trade-offs that you have to do today. And having the framework give you tools in the API to tell very precisely how you want those things handled, as opposed to pushing them into the business logic and making your processing much more complicated than it needs to be. So one way to think about it is to compare it to Lambda architecture, for example, which I assume you guys are familiar. The idea of running 2 pipelines, a stream mode pipeline, which is low latency, but without completeness, and then a batch pipeline, which provides completeness. Maybe, because again, you can have late events between batch windows. And so, that's one way that people have been trying to inject some low latency to their processing. Obviously that's not, if a solution asks you to process everything twice, that's a good sign. It's probably not the best solution. And so with this kind of framework, you still get the low latency approximate results. The same thing you get with Lambda architecture, you still get it here. But as soon as the additional data points arrive, you get complete results. So you get the complete results as soon as the data is available. You also get only one system to manage. So obviously, it's less to administrate. You pay less in resources. You have less to learn. And you have one set of bugs. That's the most important part. That, you don't have to implement the pipeline. It's the same code, so you're guaranteed to be consistent between them in terms of the logic. Ideally 0 bugs, but everything has bugs, but at least it's the same bugs, however you run it. It also makes developers more productive. It really makes you think explicitly about your trade-off. And in the end, if you think of computer science, it's really it's all about abstraction layers. That's all computer science is. It's defining new and productive abstraction layers. And we really think this is really the new productive abstraction layer for data processing in general, because every data processing is unbounded if you think about it. Even if we've learned to think about it, like we've kind of twisted our minds to think that things have to happen in batch, that's very unnatural. This is really the abstraction that does away with this unnatural assumption. And the most important thing is you do not have to re-architect. The thing that really makes me sad is when I see a customer who's written a pipeline that works, it does what they want, and then they realize, I'd like it to scale better, or I'd like it to, go faster, like I want my results earlier, or, it costs me too much money. I want it, I like the pipeline, but I want to have it cost less money. And then they re-architect, and they throw away perfectly working code, and they change to a new framework, and they, they rebuild everything. And, it's great for software engineers, it's fun, everybody likes to, write something better. From a business perspective, it's really painful. Like you really should not have to re-implement business logic that has been tested and debugged and works. You should just be able to tweak the deployment parameters, but run the business logic unchanged. And that's what you get with that programming model. So the programming model is available, as I mentioned, as an open source SDK. It's on GitHub, Apache license. Right now it's in Java, Java 7, just now Java 8. Finally, it makes much nicer syntax, as you can imagine, with with lambdas especially. There's a Python version coming soon. The way the SDK works is everything I've described here is in the SDK and has no tie-in to Google Cloud. It's just, it's completely independent programming model. To run it, you get to pick what's called a runner, which is the environment where your pipeline is going to execute. And so the SDK has a local runner, run on your laptop when you're in the plane and you want to program. As cloud, we offer a cloud service where you can submit your pipelines and we'll run them for you, and I'll describe that in a bit more details. And then there are two open source runners to run in distributed manner. There is a Spark runner, which was written by the folks at Cloudera, and there is a Flink runner written by Data Artisan. And so they both support batch execution right now. When time came to work on the streaming one, on the Flink one, well, they came back to us and said, that's pretty hard because you have a much less mature programming model for stream processing using micro batches. So nothing is impossible, but that's really quite a bit harder to provide that abstraction layer on top of Spark. The Flink one, on the other hand, my understanding is that it will soon support running Dataflow in stream mode, and you can understand why. With 0.10 coming out and with those semantics available in Flink directly, it becomes a much easier mapping. So I'm really looking forward to having the Flink runner for Dataflow be able to run not just in batch but also in stream mode to get all of those benefits in a way that's portable anywhere. Because Google Cloud only runs at Google, but all users, and I heard that in all the talks I did yesterday, people want to be able to port their pipelines, and so it's important whether on-prem in some other cloud that they be able to run that, and we're really excited to have Flink be the way to do that. So I mentioned we have a graph service. If you write your pipeline and if you decide to deploy it on Google Cloud Platform, we're going to do a bunch of things for you. We're going to optimize the graph. Basically, this is at that point you're running on the infrastructure on which Google runs its own business. And so, as you can imagine, we have years and years of experience optimizing those graphs for execution. We do worker management for you, and we're going to get some heat here. We do worker management for you, so we'll deploy the machines. You don't have to run a cluster. You don't even have to decide the size of your cluster. You just say, run this pipeline. And we'll do monitoring. So in practice, that's what it looks like. To you as a user, there's only two things you care about. The SDK, where you write your code, where you write your pipeline, and the monitoring UI, where we show you what's happening with your pipeline. And so under the cover, when you submit, we optimize the graph. We deployed workers for you. We auto-scale the workers. So it's not, it's not like a cluster-based system where you deploy a cluster of a given size and you send jobs to the cluster. With the Cloud Dataflow service, the job is the first-class citizen. You just submit a job. Whatever number of workers is needed, we'll auto-scale for you. We'll keep changing the number of workers based on the work that has to be done, and you only pay for what you need. You don't have to guess ahead of time the size cluster that you want. Obviously, you can put a ceiling if you want. You can tell us, no, don't auto-scale past a certain number. But it's really the job is the first concept. And then we monitor everything. And so that's what the monitoring console looks like. Whether you run in bash mode or in stream mode, we'll show you your pipeline as it's executing. We'll show you the logs for each of the steps. The thing that's really nice is that what you see here, this corresponds one-to-one to the code as you wrote it. These are your P transforms as you wrote them. Obviously, under the cover, we've optimized the graph, and you would not recognize the logs as they come out because we've merged and we've reordered and we've done all we can to optimize execution. But by the time it goes back to the monitoring window, we've mapped those logs back to the primitives in your code that you recognize, so you can track the progress of your job, see the logs, find the bottlenecks, and that's the only thing that you're responsible for. As an admin, you administrate your pipeline. In terms of the code you write, you don't administrate, the memory and the network and the storage and the machine deployment. All that is done for you and auto-scale by Google. It's part of a larger platform. I'm not going to describe, I'm not here to do a sales pitch on Google Cloud, but at capture time, there's a bunch of services, things like Cloud PubSub, fully managed event delivery system, many-to-many event delivery system. Cloud Dataflow is used a lot in the early processing, ingesting data to prepare it for storage. But also, since your code is touching the data, you might as well do real-time analytics on the fly, maybe do alerts, power a dashboard, etc. 3 different storage systems, BigQuery, fully managed structured storage. Bigtable, which uses the Edge-based interface, but is under the cover Google's Bigtable, and Google Cloud Storage for file storage. And then downstream, BigQuery, fully managed SQL. Just like in Dataflow, you don't have to deploy a cluster to send jobs, you just send the jobs. Same thing in BigQuery, you just send SQL statement. And then, for a few seconds that it takes to run your query, we'll give you thousands of cores working, and you only pay for the few seconds that you need those cores for, and then they reclaim. Cloud Dataflow, it shows up twice because it can be used to process at ingestion time, but also to do background processing. Cloud Data Proc, which will deploy Hadoop and Spark for you and kind of run jobs for you. Actually, just today, we are, actually that's not going to go. I'll talk more about Cloud Data Lab. So that one, we're actually announcing today. I may actually be breaking my own embargo here, I'm not sure, because we have an event going on in Paris this morning, and depending when the announcement is, the official announcement is in Paris this morning, there's a Google Cloud event. So maybe, I don't know, by a few minutes, this may be early, but I'll tell you a bit about Cloud Data Lab. And you can run Flink very well on Google Cloud, as you see it by some of the, actually this is a blog post from Data Artisan where they run matrix factorization using the alternative least square result. And so, some of the, you read the whole blog to get the full, kind of the whole information, but using 40 instances, either with 8 cores or 16 cores, being able to process almost 30 billion entries. So again, have a look at the blog, but the performance of Flink on GCE has been proven already. It's very easy to deploy. There's a tool called BDUtil, stands for Big Data Util. It's a command line tool that is going to deploy a cluster for you. So you just say, what machine type you want, what zone you want to be in, how many machines you want, and in one line you get your Flink cluster set up, configure. We start up the VMs and do everything for you. So easy deployment. So very quickly, I mentioned Data Lab. We're announcing that today in Paris. It's a Jupyter Notebook, or IPython, if you're more familiar with the old name. As a tool, it's a well-known tool, nothing Google-specific here. It's just a one-click deploy. You get your notebooks. They're backed in a Git repo that we run for you. It's integrated with BigQuery. And so within your IPython notebook, you can go run your BigQuery queries, etc. Have access to all your files in GCS. So just makes it very easy for a data scientist to interact with the system. That's it. I just want to make sure I left a few minutes for questions. So just some links here to learn more. As I mentioned, Dataflow is published as a paper. You can get from a VLDB website. The SDK, this is a Java one. As I said, the Python one is coming soon. And if you're interested in trying out the service, please go there. The service is now generally available. We went to beta in April. We went GA in August, so now it has SLA and deprecation policies, so really robust auto-scale service that you can run your business on. There's a $300 free trial. If you haven't tried Google Cloud yet, then you can apply for the free trial and use that for anything you want. I would suggest that Dataflow as a very good thing to use it on. And please let us know what you think, and thank you very much.
Yeah, hello, thanks a lot for this great presentation. My question is the following. If I got it right, for Google Dataflow, it's one single API, 2 execution engine, Flume, Java, and Millwheel. While for Flink, it's 2 APIs and 1 single engine. So what's your take on this? Can we dream of a world or imagining a world where it's 1 single API, 1 single engine? Thank you.
So just a small correction. It's not. You're right. It's mostly 2 engines. At some point, it's a gray zone, right? Because you could make it 1 engine with a bunch of if statements. I mean, it's mostly 2 engines internally. It's not Flume and Millwheel anymore. It's the next generation of that. So, but it's obviously heavily based on Flume and Millwheel. That we've built it that way. I mean, you could do it either way. As Flink runs it on the same engine. From our experience, that's the way that's the way we've run things at large scale, is really to optimize for the different environments. And so that's how we run it internally. Depending on the scale you run on, you may be able to run just on the stream runner and run your batch computation on that. That's not the way we do it right now. It's, that may be how we evolve it. Again, depending on the amount of data you're processing, the optimization makes more or less sense in either mode. So to some extent, that's pretty much irrelevant. I mean, that's a good discussion to have as technologists. For our users, that's irrelevant. To them, it's one service surface. And how we do that internally, how we choose to optimize, how much of the code is reused between the two, and how much is different code, is not really something that users have to worry about. But from a technology discussion, it's very interesting to really compare the optimization and really think through. Do you really need to have two different systems to run that? I think it's TBD. 5 years down the road, how things will have evolved, will they have further specialized or come together? We'll see when we get there.
Hello, for the late firing of the events that you mentioned, and you also mentioned that you can fire the last set of events. For example, you fired event 1, 2, 3 like half an hour back, and now event number 4 has occurred. So you will fire 1, 2, 3, 4 as aggregate. So you will be remembering all the past events of the windows that you have already triggered, right? So is this window to remember the past triggers, is it configurable, and how does it work internally? Yeah, it's configurable. Obviously, we can't remember every single data point for the last 10 years. And so you tell us when to stop remembering, and you configure that, and to whatever value you want. And so if we get a late event, if the window closed a year ago and we get a late event, we'll still trigger, but we're not going to be able to give you the old data. So if your triggers, if your late event strategy is to accumulate, that's fine. If it's to recalculate, well, sorry, you're out of luck. So you tell us when to stop. Yeah.
Some more questions?
Sefaridi from 6 in Sweden. A question regarding the auto-scaling. Does the user have to specify some kind of service level objectives to help in the auto-scaling? For example, saying, I want that amount of throughput, or...
Yeah, so in auto-scale, you can tell us how aggressively to auto-scale. Yeah. You can, that's where costs come into play. Exactly. Running in batch is cheaper than in stream. And in both modes, you can decide how much you want to auto-scale. And so you can put a ceiling. I mean, the thing is that because we actually charge, we don't charge you for the hour, like a VM, we only charge you for the time you use the VM. So assuming you're still going to process all the events, it actually doesn't cost a lot more to auto-scale more aggressively because you're just going to be processing your events more quickly. At the end, you're paying for the time you spend processing. And that's kind of the beauty of cloud, that you get the scale almost for free because you're paying on the amount you're processing. It costs you the same if you're processing it all at once or slowly over time. It's not exactly true because we have a discount that we give for sustained use. So if you use machines for long periods of time, you get a small discount. So it's a little cheaper to even out, but it's really not that big of a difference. And so that's really the beauty of cloud, is it doesn't really cost much to be more aggressive in providing low latency.
So you presented data flow in 2 places, one in analyze and one in processing. And I think of it as analyze, building a machine learning models, and processing is applying the models, predictions. Do you have any plans in this area?
So Dataflow right now is not optimized for iterative algorithms. So that's one reason why you'd want to run on Flink, for example. Dataflow is more around kind of high throughput processing. And so that's, that kind of example would be done more, at ingestion time. But, there's a ton of stuff we write on MapReduce. We used to write on MapReduce internally. This is just replacing those kind of engine. But yeah, it's not optimized right now for machine learning or graph or any kind of iterative algorithm.
But still, can I maybe learn another system and apply the predictions in Dataflow?
Yes. So you can call your predictions from Dataflow. Well, you mean you want to train another system and deploy the model? Yeah, you can do that. You can deploy the model and run that in Dataflow. Yeah. Do the predictions in Dataflow and train your model separately. Yeah.
So you mentioned that you're focusing more on the high throughput processing. What about the processing between streams, like joining streams, or the code group things that Flink has today? Whether is it available in the API, or it will be available, or what?
Sorry. So what feature in the API?
The joining of streams by key, for example.
Joining of streams by key?
Yeah. So
Yeah.
even if you have a key, a stream by session in one stream and another stream with the same session, and then you want to create another streams using the same.
No, that's there today. You can join streams. Yeah. No, so that's there today. That's fully supported.
With the semantic of waiting, again, the time. The problem when joining streams is actually sometimes you have to wait, things like that.
And so it's also when you do, you don't have to worry about. When you do a time window based on event time, if one stream is 2 hours behind the other stream, well, we'll do the waiting for you. Like we'll match those events, and only when we get those events, aligned, are we going to trigger your window. So all that is taken care of for you today.
Yeah, so a question about the auto-scaling and the configuration of the job. What if you were to have a job that had a really big mapper in it that requires a lot of memory?
A very big what?
Like, imagine a map step, something that has a key with a huge number of data points in it, and it actually requires a lot of memory on a single machine, because that's the way the data looks like. How does Google handle that? Can it actually auto-configure the amount of memory per machine?
Yes, but yes, you're able to configure memory. You get to choose the worker types that get used. But actually for that, even up to a point, there's only so much memory you can have on a single machine. So there is, how can I say? I can't give details, but there is a lot of work going on to make that go beyond what a single machine can do. With the same constraint, you still have to reduce that on one machine. So I can't really say that much on that, but that's something that you can expect to be pleasantly surprised by pretty quickly. Yeah.
Hello, and thank you for the great presentation. I have a question about the watermark definition. I'm curious about, because you said on your slide that's often heuristically defined, but from the discussion and from the way it's presented, it looks like it's more like machine learning. So can you give us some more insights on how this is actually done, how the system defines watermarks he has to wait? Thank you.
So actually, yes, there are several strategies, there are several algorithms, several heuristics that we use, depending on the source. Like internally, we use that a lot with Google internal sources like logs. And logs, we have a very good signal about what's happening upstream and delays and network delays. And so, we have a set of heuristics in those situations where we have good visibility. We have other heuristics where we have no idea. Where things are coming from mobile devices, things are coming from others. So machine learning is definitely used in some of those. It's a library of heuristics, and we keep trying them out. Optimizing, learning, and changing them. So, like at any point in time, we have a library and we pick the right one based on the patterns that we see in the events. So sorry not to be that much more precise, but there's a lot of variety in how the heuristic gets determined, and that's a lot of the secret sauce is being able to get those signals and then have the experience and learn how to set the watermark based on those signals.
Hi, can you configure dynamically the watermark? Because if the stream becomes slower or becomes higher, can you dynamically modify the watermark?
Sorry,
can you modify dynamically the watermark?
Yeah, well, the watermark automatically adapts. So as it sees delays build up, it kind of learns from what it sees and adapts to the stream. So you don't manually modify it. If what you're asking is, can you manually modify it? No, the watermark is kind of a contribution of the framework. It's our best guess. Now, you can manually set the triggers. Maybe you can watermark. Those guys have no idea what they're doing. Yeah. I'm going to set my triggers myself. And that you can do, but you cannot modify the watermark. Okay. That's basically our best guess.
So we have time for one more question. Yeah.
So you said that how things are actually executed and optimized is hidden from the developer. Does this impose some problems for debugging? Because basically when I write a program, I'm not sure how it's actually executed, and there could be some things that break my logic.
And so that's true. That's a general problem of optimize things in general. And so that by doing that, it really puts the onus on us to give you the tools to do that. And that's why we've put so much effort into collecting all the logs and bringing the logs together. Even if the worker has been reclaimed, all the logs are brought back together. They correlate it back to your to your code to give you as much as you can. I think this is something that we're still working on, because you're right that as you may, debugging something where you don't have access to the fully optimized pipeline, at some point you're going to run into issues. It's a compromise we're comfortable with, because that's what we do already internally, where when we have those abstracted frameworks, the team that writes it very often actually, even though we're all at Google, they would have access to the Borg logs and kind of detail. They actually really aren't equipped to go debug that, and so they go through the platform. And then they just put the request on the platform team to help them debug. So we've learned a lot around what it takes for our internal users to debug those kind of situations, and we've brought that to Cloud Dataflow. But I think it's not a solved problem. I think it's an ongoing, it's something that we're always working on, because there's always going to be like the corner case where the user just cannot figure it out, and they have to go to us and ask us to figure it out. And so we use Stack Overflow, we use support channels, we use support groups to do that, and when those happen, like we get all over them, because we realize that people cannot solve those. They're pretty rare. I think most of the issues can actually be easily diagnosed using the tools we give you. But you're right. It is always a problem of having those kind of opaque systems.
Yeah, I think the rest questions can be done offline.
Okay.
I think we have to move on to coffee break.
All right. Thank you very much.